So most students are fine with vertical forces, but as soon as a force comes in at an angle like this one you're looking at with the 10 kilonewtons, everything starts to fall apart. So in this video, I will walk you through this question step by step to help build your confidence around questions such as these ones. Now, I've intentionally left out some of the labelings because I want for us to do that step by step as well, so you get the full understanding of where some of the values will come from and why they exist. So as usual, the reaction forces. So to the left, I'm going to choose this to be RA, and to the right, I'll choose that to be RB. And I'm going to make the full length of this beam as 5 meters. And in between each force, so starting from RA, I'll make that 2 meters long. And also between the 10 kilonewtons and the 8 kilonewtons. Now, one very important thing that we need to do is to look at the reactions for the supports, because a lot of times I see this part get neglected. So let's just look at it real quick. So to the left, we have what's called a pin support or pinned support. And what it does, it prevents movement in the horizontal and vertical direction. So because of that, we'll have a vertical reaction. So that's my vertical reaction in the Y direction. And we'll also have an horizontal reaction like that. That's in the X direction. So RA should have 2 components there, vertical and horizontal. And I'll show you how to resolve them shortly as well. And then when we go over to RB, now because RB got this roller, so you should see the 3 circles at the bottom of the triangle there, that means it's a roller support. So it allows for some sort of horizontal movement to take place. So what that leaves us with is just a vertical reaction. So this arrow represents that. So the vertical reaction in the Y direction for RB. So that's the supports taken care of. Let's go to the forces now and resolve them. So first we need to resolve the 10 kilonewtons inclined force. And we're going to resolve that into horizontal and vertical components. And we see where the force is acting at an angle of 30 degrees. So what I'll do, I'll just draw sort of a dotted line just for you to see where these forces are. So this is a trace of the horizontal component. It's going to act at the same point where the tip of the arrow is. And in addition, this is going to be a trace of the vertical component. So it's 2 force components we're going to have there. That's what we're going to resolve now. As usual, you would have seen this formula before. So for the horizontal component, so Fx, it's going to be the force and cos the angle. So we have a force of 10 and cos the angle is 30 degrees. So this leaves us with, so that's 8.66 kilonewtons for that part. And then when we do the same thing with the vertical component, we'll just have here force, sin, angle. Our force is still 10, and sin, angle is still 30. So this leaves us with a force component of 5 kilonewtons. So for that 10 kilonewton inclined force, our horizontal component is therefore 8.66 kilonewtons and our vertical component is 5 kilonewtons. So I'd really recommend at this point to redraw the free body diagram with these updated forces, and the only thing that would change is at the 2 meters from RA, you would now have this purely vertical force of 5 kilonewtons. And an horizontal component would be there as well of 8.66 kilonewtons. So I'd always recommend that you redraw the free body diagram if you can't visualize it. So we're going to apply horizontal equilibrium, and this will be relatively straightforward. So what this should be is the sum of the vertical forces, so Fx for vertical forces should be equal to 0. So we're going to effectively sum the vertical forces, and they should sum to give 0 to suggest that the system is in equilibrium. So before we start to sum these horizontal forces, let's take our sign convention that forces going to the right will be positive and to the left negative. So we have only two horizontal forces. So we have this RA, so I'll just write that as RA, and subscript X, which is our unknown, that's going to the right. And we also have this component of the 10 kilonewtons, which is the 8.66 that we found, so that's going to the left. So it's RAX minus 8.66, and that's what equals 0. So therefore now RAX will be equal to, if we were to solve this equation, it's just a positive 8.66 kilonewtons. So that's representing our RAX. So before we find our RBY and RAY, I'd like to just inform you that if you would like any one-to-one support, the link is in the description for you to check out. Okay, so we now have two unknown left. We have RAY and we have RB, reaction at B, Y, so both vertical forces. And you're probably wondering why we don't just sum the forces going up and down, and that's actually a valid option, but because we have two unknown forces in the vertical direction, we can't do that at this stage. So we're going to have to resort to another equilibrium equation. So we're going to take the moment about a point, and we're going to choose that point. And the point I'm going to choose is, I'm going to go for this point here. I'll highlight in purple this point right here. So I'm going to take the moment about point A. So that equation is the sum of the moment about point A should be equal to 0. So the reason I've selected point A as well is because it does two things. It actually eliminates the reactions for RAY and RAX, because those reactions act through that point, so therefore it would be equal to 0 if you were to do the calculation, because the formula for moment is force multiplied by perpendicular distance. And because we're taking the moment about point A right there, then the distance of those points from themselves would effectively be 0. So therefore, we've nullified those forces and we've left with only forces that will have some sort of effect, moment effect. Now, in the past, I've shown you how to do this using a system clockwise moment equals counterclockwise moment. I'm going to just use a different method this time just to give you some sort of variety, but it's gonna level out to give the same working anyways, but it's good to sort of introduce some other new elements. So I'm going to take counterclockwise moment to be positive. So counterclockwise moment I'll take as positive, and clockwise moment as negative. So what that means is any force that is going to rotate or give the effect of a counterclockwise rotation. So for example, RB, this reaction force is going upwards right there at RB, is going to have this effect. So it's going to rotate in a counterclockwise direction. So I'll take that as positive. And the 8 kilonewtons, for instance, it's going to do that. So that will be negative rotation. So that's positive there, that's negative. And the same thing will happen right there with the component of that 10 kilonewtons. It's going to go that clockwise direction. So I'll take that as negative. So what that gives us is our force times perpendicular distance now. So starting with RB, so RBY to be specific, will be multiplied by its distance from RA. It's already perpendicular, so we'll have RBY multiplied by 5, and that's positive. And next we will have the force component. Well, I'll just go across to the 8 kilonewtons. So we'll have that 8 kilonewtons that's going clockwise, and I said that will be negative, so we'll have minus that 8 kilonewtons, and its distance is going to be 4 meters away from RA. And then finally, this is where you have to be very careful, because we're not using the 10 kilonewtons, we're using the vertical component that we have right here, that 5 kilonewtons. So it's going to be 5, which is our vertical component, multiplied by 2. And all of this equals 0, because the system here is in equilibrium. So let's solve this equation then. So what we have is 5 times RBY and minus 4 eighths and 5 2, so that's minus 42 equals 0. So therefore, if we were to just divide our 42 by 5, we'll get the answer for RB. So RBY equals, it should be 42 divided by 5. That's going to give us, so that's 8.4 kilonewtons. So that's RBY, and our next step is to evaluate what RAY is. And before we do that, if you could give the video a like and just share it with someone you think it might be useful to, then I would really appreciate that. So we have found so far RAX and we have found RBY. So the only unknown that we have now is RAY. And to do that, we're going to apply another equilibrium equation. So we're going to apply vertical equilibrium. So with this, the sum of the vertical forces should be equal to 0. So forces going upward should be equal to forces going downward. And for this, I'm going to take upward forces as positive and downward forces as negative. So if we just get a full view of our diagram again. So what's going upward? Now we have RAY, so that's our unknown. So we have our RAY going upward. We also have RBY going upward, so that's positive again. So RBY going upward, that's positive. And going downward now, we have that 8 kilonewtons, so minus 8. And we have that vertical component that we evaluated right here, that 5 kilonewton, that's going downward. So those are all the vertical forces that should sum to give 0. Now we previously calculated RBY, so that leaves us with only one unknown, and that's RAY. RBY was 8.4. And if we sum these two up, we have minus 13 there, and equals 0. So when we do, this is going to work out to give 13 minus 8.4. So therefore, our RAY should give us 4.6 kilonewtons. So I hope you found this video useful, and if you have, then just share it with someone who needs it.